You have probably noticed it too. PEBA filament is suddenly everywhere, and it feels like the new must-try flexible material in 3D printing. But maybe you've also seen the price tag and thought, is it really worth paying 3 or 4 times more than TPU? Or you've heard it's softer, bouncier and maybe even tougher, but still wondered what the real advantage is? In this video I will run hands-on tests that show when PEBA is the right choice, reveal the one hidden advantage of PEBA nobody's talking about, and share the key tricks for printing both filaments successfully. So you can cut through the hype, avoid wasting money, and know with confidence which filament actually belongs on your next project. Hi, my name is Niels and you're watching Perspective 3D. When Siraya Tech offered to send me a sample of their PEBA filament, I'll be honest, I had no idea what it even was or why it might be different from TPU, the go-to filament for flexible prints. I did some research first and I came across one key fact. It's crucial for understanding the rest of this video, and it explains why PEBA is so different from TPU. If you take a piece of TPU 95A and stretch it with your hands, it tears pretty quickly. Sure, it bends nicely, but it doesn't take a huge amount of force before it breaks. The same piece of PEBA 95A doesn't break nearly as easily. I could stretch it much further. Instead of snapping, it actually started cutting into my hands. Why is that? The answer lies in the chemical structure of both materials. TPU's backbone is polyurethane. That gives the filament decent flexibility, but its strength under tension is limited. PEBA, on the other hand, is what's called a copolymer. It combines chains of flexible polyether blocks with very strong nylon blocks. And that combination gives PEBA a completely different set of mechanical properties. But that's not all. PEBA isn't just a tougher version of TPU. Its internal structure also changes how it stores and releases energy. And that's what I wanted to test first. But before I could do that, I had to solve another problem. How do you even set up a printer for PEBA? For TPU 95A it's easy. You will find profiles right inside Bamboo Studio or Prusa Slicer. But for PEBA, nothing. Not a single profile. So I went to Siraya Tech's homepage and luckily they had me covered. Not only did they provide detailed guidelines on how to handle the material, they also had ready-to-use profiles for Bamboo Studio and Orca Slicer. Basically, PEBA needs to be printed a bit hotter than TPU to ensure a good flow. The nozzle temperature should be higher, and the heat bed should sit around 100 degrees Celsius to prevent warping, which already hints at the nylon component inside PEBA. Like all flexible filaments, AMS feeding is out of the question. You need to feed it directly. Siraya's guidelines also say drying is mandatory, so I dried the filament first in my new Chitu Dryer, and then connected my dryer straight to the printer to keep it dry during the print. When I compared Siraya's PEBA profile to a standard TPU profile, the difference were clear. The PEBA profile has a higher volumetric flow rate, which means it will end up printing a little faster than TPU. Retraction volume was also bumped up, probably to reduce stringing and oozing, and of course the nozzle and bed temperatures were set higher. But before we dive right into the tests, I like to cover another very important topic. Is it safe to print those materials without an enclosure and filter? With TPU, there are studies showing that certain organic compounds are released during printing. For PEBA, I couldn't find any solid data yet. And that's why, in my opinion, it's better to play it safe. Even though an enclosure isn't required for the printing itself, I would still recommend using a closed printer with a proper HEPA and carbon filter. If you print on an open machine like I do, make sure it's in a well-ventilated, dedicated space and run an air purifier as well. I will link my setup in the description. So here's the takeaway. You can start with a standard Flex or TPU profile, but for PEBA you need to at least increase the nozzle and bed temperatures. Use a satin or textured plate and just skip the glue. With those adjustments it prints beautifully. And once I had my setup dialed in, I was ready to answer the first question. Does PEBA actually bounce higher than TPU? I printed several different versions of these balls and dropped them one after another, measuring how high they bounced. This would finally show whether PEBA is really as bouncy as everyone says. If you squeeze a TPU ball in your hand, it feels soft and flexible, but when you drop it from a height, it usually just hits the table with a dull, heavy sound and barely bounces. So for my actual test, I made 5 different samples. A PEBA and TPU ball with 100% infill and 3 walls, another one of each with 15% infill and 2 walls, and then a TPU ball adjusted to 1.5% infill to match the lighter PEBA's ball weight. And here's the difference. While the TPU prints fall flat with a rebound height of around 11 centimeters, the PEBA balls didn't just bounce twice as high at 22 centimeters. Even when I match the weight of the TPU ball, PEBA still takes the win. So no matter how you print them, a PEBA ball always rebounds higher than TPU. PEBA clearly wins on energy return, making it the overall bouncier filament and therefore the perfect choice for one specific application: RC car tires. But for a good tire, bouncing alone isn't enough. What tires really need is grip. And to see which one performs better, I set up a simple test rig with blocks of TPU and PEBA. Each block was placed on a smooth print sheet with a 5 kg weight on top. Then I pulled them with a force meter to measure the resistance force during sliding. And the results were pretty clear. The TPU block showed about 70 newtons of resistance, while the PEBA block measured nearly twice as high. And that means PEBA doesn't just bounce higher, it also delivers roughly twice the grip compared to TPU. And that gives it real potential for printing tires in RC applications. But while I was playing around with the tires and the bouncy balls, I noticed something else. TPU and PEBA don't just differ in bounce or grip, they even feel different when printed with the same infill. To dig deeper, I printed a set of test cylinders with different infill percentages. Then I placed each one into this fixture, applied a constant load of 5 kilograms and measured the remaining height of every sample after 1 minute. With TPU, the trend was clear. Even at moderate infill levels, the parts stiffened up pretty quickly. Samples that should have felt flexible started behaving almost like rigid plastics, with almost no compression, already at just 7.5% infill. PEBA, on the other hand, behaved a bit differently. The data itself doesn't show a dramatic difference, but when you actually handle the parts, you feel it straight away. Even at higher infill, PEBA still keeps a bit of softness and give instead of turning completely stiff. A TPU cylinder printed at 15% infill barely flexed at all. It felt closer to a hard plastic than a flexible filament. And the same cylinder printed in PEBA though still compresses slightly and springs back when you release it. And that's why PEBA is used in high-performance products like running shoe soles. They need to be soft where it counts, but firm where it matters. But that instantly raised another question for me. Shoes don't just get used indoors at room temperature. They are exposed to heat in summer and freezing cold in winter. So I wanted to know, what happens if we take those same test cylinders, freeze them at minus 18 degrees Celsius, and then put them under the exact same 5 kilogram load as before? At room temperature, both TPU and PEBA collapsed under load once the infill was low enough. But straight out of the freezer, the story completely changed. The TPU sample turned rock hard. It didn't collapse at all under the 5 kilogram weight, and instead, it just sat there stiff and only started to sink in slowly as it warmed back up. PEBA, on the other hand, behaved almost exactly like it did at room temperature. Even at minus 18 degrees Celsius, it flexed and compressed under the same load without turning brittle or stiff. And that was the moment it really clicked for me. PEBA isn't just stronger or bouncier, it stays reliable even in extreme cold. And think of the possibilities this opens up for your projects. Imagine printing your own bike handles. They will feel the same in blazing summer heat or freezing winter cold. Or using multi-material printers like the Prusa XL or the upcoming Snapmaker U1 to create jointless grippers with PETG and PEBA. Or this bracelet here, printed in PLA with a flexible PEBA core. And the best part? Thanks to PEBA's strength, it isn't just decorative, it actually lasts. And if you'd like to see a full tutorial on how to design and print multi-material projects like this, drop a comment below and subscribe so you don't miss it. After all these tests, I think it is clear that PEBA has unique advantages. But before you rush to buy it, there's still one elephant in the room we need to address: price and availability. PEBA costs about 2 to 3 times as much as TPU. The color range is very limited and only a handful of manufacturers even offer it right now. TPU in comparison is cheap, widely available, and more than good enough for most casual projects. If you just want to print toys, brackets, or simple flexible hinges, TPU will absolutely do the job. But if your part needs to handle stress, outdoor use, or freezing temperatures, that's where PEBA is worth the investment. I really enjoyed experimenting with the PEBA filament from Siraya Tech. So if you want to explore its advantages for yourself, check out the links in the description. And honestly, I think the real hype around PEBA is only just beginning, especially once multi-material printers become more mainstream. And while you're waiting for your order to arrive, take a look at one of these videos next. Your subscription helps this channel grow. Thanks for watching, and I'll see you in the next one.